So the last thing I want to do, I think this is the last thing. I want to have two papers where I want to talk about how you can talk about binding. Solubility products, you're talking about binding, you're talking about Ks of the binding of the solubility reaction, which is sort of the reaction of it binding itself in a sense. But the main theme of this test is going to be K is related to G, H, and S. And so I promise you that one of these examples is going to basically be there for you to recreate. So take notes. We have two cases that both involve zinc binding. We have a sulfur-rich metallothionein protein, and we compare lead versus zinc binding of that. And then we have zinc binding one of those designed proteins that we had from Chapter 2. There's a study about how zinc binds those proteins, but it's relative to sulfur disulfide bonds that are sort of holding the protein, and when they're formed, they hold the protein in place. Two slightly different things, but both of these give us thermodynamic data that we can interpret in light of chapters 1 through 4 in Atkins. So here's the example of, this is a picture of a metallothionein, and its really only job is to sit there as a sticky, it's like fly paper for sulfurs. Because what it does is it has a bunch of cysteines, a bunch of sulfurs, and it's fly paper for zincs and leads and anything that has that's not soluble, anything that is not soluble that has a insoluble sulfide will stick to sulfur. The two things are connected, okay? And so here's a bunch of metals. These could be zinc or lead. It doesn't really matter. What matters is that you have a bunch of sulfurs. And the way the body uses these, by the way, is it has zinc transporter proteins that move stuff in and out of the cell. One of the ways it keeps the concentrations in the cell in the right place, remember the Irving-Williams series says it needs to be in a certain place or else it will stick to everything. So what it does is it sends out flypaper proteins to mop up the extra sticky zinc. And that's what the metallothionein does. It sort of patrols around and it binds lead, it binds zinc. And, you know, lead is not good for life because it's very sticky. And so one of the things these do, these are protective because they go around and they stick to the lead before it can stick to your neurons and stuff like that. Okay? And the neurons have a lot of these because they need to protect themselves against the stickiness of random metals. Okay? So what they did is they actually took lead and zinc, and you see that there's a lot of physical chemistry right here. Now they found out that the lead and zinc, there's multiple binding sites. And so there's a first binding event, second binding event, third binding event that happen. And in order, these are weaker binding events, like the strongest binding site gets filled first, okay? But the cool thing about this is that they did it under different temperatures, I believe. Yeah, one way or another, they did it under different temperatures, and they determined not just a delta G, but also delta H and T delta S. So if you look up at these, let me just ask you the kind of questions I could ask you on a test. Let's say, okay, which binds more tightly, lead or zinc? You've got to look at the three, but you can sort of compare the first to the first and second to the second and things like that because it's pretty consistent. Which binds more tightly to the metallothionein? Is it the lead or the zinc?
It's K where the bigger it is, the tighter it binds.
Yeah, it's a K of association where the product is, the product in this case is the bound. That's a really good question because it would be totally different if it was a dissociation K. This is a K of association.
So the lead binds more tightly.
Yep, totally. And it has the larger negative delta G for binding, more spontaneous event. They both bind really well, don't get me wrong, you know. So what drives the binding, entropy or enthalpy? So first look at zinc. And just say overall, I mean, we had three different binding events, but when you break it down in delta H and negative T delta S, this delta G equals delta H minus T delta S, so we can say which of those numbers is bigger. And that would be the one that drives binding, bigger and negative, I should say, because it binds binding, it drives binding. So would you say that lead binding is enthalpy driven or entropy driven?
Well, the entropies are all negative. It's good because the fat.
No, that's good. Remember our delta G's are negative,
Oh, okay.
and we're putting, it's actually, don't look at this. Always look at it in the T delta S. They're giving you this because delta
T
S.
delta S.
Yeah, yeah. So they're doing this. That's what I want to show you here. They're giving you this to help you.
Okay, so those are less negative kind of than the zinc.
Right, right. And just looking at the lead,
So the delta G's will be less negative. Because you're subtracting a
if you,
positive number from a larger negative number.
right, right. The one that really stands out as different from the other five is this one right here, right? So this is the one that we want to talk about second. But first we can talk about the delta H's are pretty much around zero. It's kind of, enthalpy is not really doing anything. What's really doing something is entropy is actually helping you, which is kind of interesting because for an association reaction, you have multiple things floating around in solution, and they're coming together to do the opposite of spreading out. But that's not the whole picture. There's also water molecules, and apparently those water molecules and all the other sources of entropy, apparently that's spreading out enough to have this be an entropy-driven reaction. Even though you have the metal is not spreading out, there must be other stuff that is spreading out. And you see that that's the case for basically 5 of these 6. But then you pointed out this one right here is a little bit different. It's still entropy driven, right? You still definitely have entropy being the main thing going on. It's just that the enthalpy is much bigger. In fact, it's so big, the enthalpy positive is bigger than the negative delta G. So that means that the T delta S has to be twice as big as this. You see, it's really entropy driven. This number is really big and much bigger than anything else. The first zinc binding event is extra entropy driven. And so does that would surprise you if you were just thinking about the protein and the metal. But there's also the water, there's also different conformations of the protein, there's all sorts of things that can be going on.
Does this have to do with when you're binding two molecules? I think you talked about it biochemically. With the water is becoming more random, I guess.
Yeah, exactly.
The water is increasing.
And the important thing to notice about that, we talked about that with the hydrophobic effect, right?
Do you have two things, like the water is like more solidified against them, where if they're
Yeah.
coming together, there's less of that, if that makes sense?
I mean, think about these waters right here. If this is a zinc or a lead, it's surrounded by these waters, and the waters see this strong positive charge, they turn their negatives toward it, and they have this, they're kind of frozen in space too. This isn't even hydrophobic. This is hydrophilic.
You're releasing the water
Mm-hmm.
by binding.
And the freedom that this water gains is apparently a greater factor for entropy than the freedom that the ion gives up by binding to the sulfur. And the cool thing is, like evolution figured it out, and we get to scratch our heads and say, okay, so this means that our picture of entropy has to always include the water. It can't just include the metal and the protein. Okay. This is a really great example of entropy-driven binding. In fact, I had a professor when I was, the professor I was working for when I was doing research, once said, I don't understand how entropy-driven binding can ever happen, because I was doing thermodynamics and I was finding a lot of entropy-driven binding. And he thought that was weird. And now that I see this, I'm like, it's not so weird. Even this can be entropy-driven. Another case for how entropy affects binding is actually another case for zinc binding proteins. But these are the ones from chapter 2. And so if you look back at that figure, they might look a little familiar. What really matters is remember that these proteins will bind zinc. And so what they did is this is what resulted in the accidental enzyme, but they kept working on the one that actually bound zinc and made tetramers and stuff like that. And it turns out that each of these proteins, they worked at the form of the protein with a bunch of disulfide bonds in it. You see how the tetramer has 1, 2, 3, 4, 5, 6 disulfide bonds in it that they would either make or mutate away. And it also binds 4 zinc. It binds 1 zinc per unit, per monomer. what they notice is that these are joining it together, and these make the molecule more rigid. And they wanted to see, how do these affect binding? These are somewhat close to the zinc binding sites, but they don't directly participate in binding. What they do is they take the whole thing and they bind it together. They hold the whole protein together. They don't directly participate. How do they affect? So what they did is they went through and they added in these disulfides one by one, okay? And they measured zinc binding delta G, delta H, and delta S. Now the only thing that they do for this, they don't help you with this one. They don't give you a negative T delta S, they just give you the delta S. But you can still compare within each column. It's just hard to do this. So what happens to binding as they add disulfides? It still binds, right? It's still a negative number. It becomes a less negative number. And so binding weakens, is what you would say. And just a little side note, if I ask you to calculate T, do you see how you would do it? Do you see the equation that you could use to take these three numbers? Right. Right. You'd plug each of these in and you should get the same number for each. So we could calculate what T is. Probably T is going to end up being 25 Celsius. I'm not sure because I can't do the calculation in my head, but we definitely could get to it. We have 4 parameters in 3 parts of an equation. It would have, all of these would have to be done at the same temperature. So it would have to give you, the single constant temperature because the calculation would become invalid if there was a change in temperature. Technically, the technique that they're using actually changes temperature, and then they calculate what the parameter is at a temperature in the middle of the range. So technically, temperature is changing, in fact, but they're reporting these all at a constant T. So what happens to entropy versus enthalpy then? If binding gets weaker, and we have the delta H and T delta S, look at what's going on with this, just within each column. Delta H, there's 2 things to notice about it. Is it positive or negative? It's positive, right? Is it getting bigger or smaller? So is it becoming more or less favorable to binding? Is it helping or hindering binding? It's positive, but it's getting smaller. So that's actually helping binding. So enthalpy, I mean, it's actually, technically, it's getting in the way less. You know, that's another way to look at it. It's less in the way. Entropy, on the other hand, because this is a large negative number, you see that we have positive numbers, and these are actually in kilojoules, so these are actually pretty big numbers when you look at it. Usually entropy is joules per Kelvin mole. But if you look at, don't worry about any of the other stuff, just look at the column itself. What's happening to entropy as we introduce disulfide bonds? Yeah, the entropy of binding is decreasing. And so they interpreted this as the disulfide bonds are taking away my entropy of binding. They're getting in the way of the binding event by holding the protein together. Okay? Oh, the other thing I should point out about this is the free energy for this equation. Protein plus 4 zincs goes to the protein-zinc complex. And so you could write this as a K, right? You put this on top, put these on bottom, and don't forget to do the exponent 4 for the zinc. Okay? But you follow the same rules for this as you do for everything else. So this is how they interpret it. And they interpret it that zinc binding squeezes the disulfide bonds, and when you have both zinc and disulfide bonds together, it strains the protein. And that means you have a less favorable entropy. It's still entropy driven. It's still the major negative free energy component, right? But it's smaller than it was when you had fewer disulfides. And they even go down to say, oh, this is where we think the disulfides are strained. They actually show the strain. That doesn't matter so much to us, but you can go down to the molecules and you can say things like that. So just notice like this, zinc coordination is significantly more exothermic. They say this because of the 10 kilojoules per mole, and that's true to say. It's less of a positive number, and that means it's significantly more exothermic. It's still endothermic, but it's significantly more exothermic. Does that make sense to you? That they can say things that way. It's endothermic because it's still a positive number, but it's less endothermic, therefore it's more exothermic. I thought that was a weird way for them to say it, and I had to check them 3 times to make sure that they were doing the right thing. Yeah, well, let's look at what they say, which it says the coordination of zinc is significantly more exothermic. And they say exothermic, and then they give you a positive delta H. Technically, that's endothermic, right? And it is, but all 3 of these are endothermic. This one's more endothermic. So that means this one's more endothermic. Therefore, this one's less endothermic. Less endothermic means more exothermic. I'm pointing it out because I think it's a weird way to say it. So if it kind of makes you scratch your head, that's deliberate, right?
They're kind of saying it like relatively.
Yes, exactly. It's all, and anytime you talk about endothermic,
Focused on enthalpy.
yes, yes. It's just focused on enthalpy, and it's just focused on comparing these 3 cases. So don't be, it looked like a typo to me at first. I was like, they got that wrong.
Yeah.
But they actually got it right. They just said it weird.
So
Yeah.
as you add zinc.
Well, in each of these cases, you're adding zinc. You're adding disulfides.
Disulfide bonds.
Right.
But as you do that, enthalpy decreases, which is exothermic.
Bad enthalpy, yes, exactly. It becomes more exothermic, and that makes, in terms of enthalpy, it's getting better, but entropy is getting much worse.
Yeah.
And that results in a delta G so this is exactly the kind of thinking that you need to be able to do. This is what the test is about.
For the exam,
Mhm.
would we print out the table? Or show our notes or like?
No, what I would do is I would give you the table, and I'd give you the things, but I'd want you to repeat what we just said. I might ask a question. Is this sentence a typo or not? Why or why not? That would be the kind of thing that I could ask. So I would give you everything you need as far as details go. It would be a question of interpreting the table correctly.